And yeah, so again, it's a great pleasure to be here. So I visited Hong Kong a few times since I moved to Japan, but this is the first time I'm visiting CityU Hong Kong. And also, I'm very happy that to be invited by Anderson Shum. And in addition, I've seen many familiar faces and with my former connections. So here's a brief background of myself. So I've been at Okinawa Institute of Science and Technology for 10 years and 3 months. And so before that, I was born in Shanghai. I grew up in Shanghai, but most of my higher education and research career has been kind of rooted in the United States. So a little background of kind of what I studied, theoretical and applied mechanics. So we had some connections with Anderson. So when I did a postdoc at Harvard University. And then I was an assistant professor at WashU in St. Louis before I moved to University of Washington. So my building mechanical engineering is next door to material science next door. So you guys had a nicer building. But since August 2014, so I moved to Okinawa, Japan. And so I've been leading, so at OIS, we do not have departments. We're a very small university. We have about 93 professors. And we do not have departments. Everyone, so before we joined the university, we're asked to name our unit. And so this is my unit name, Microbial Nanofluidics, because the fluid mechanics unit, the name was taken by a professor working on turbulence, and he arrived a year before me. So I have to find something else. So I was able to capture all the work I was doing and I plan to do. So the research, so in my group, we're mostly focused on fluid physics, but at small length scales. And so we're interested in both fundamental research, but also applied with relevance to biotechnology and some industry collaborations. So the movie here, this is actually a pretty interesting, this is the OIS logo. It has a lot of Okinawan and Chinese connection. So we call this as shisa. So it's kind of half lion and half dog shape, representing prosperity, good luck, and so on. And so this is a small microchannel we fabricated at OIS, our core facilities. Okay, so being the provost, I'm required to give a 5-minute quick introduction of our university. So let me jump right into that. So where are we? So we're actually kind of in the middle of nowhere. So we're pretty far from mainland Japan. We're closer actually to Hong Kong, about 2 hours away, but we're closest to Taipei. It's about 1 hour flight. And so Okinawa is famous for longevity with good food, with a lot of antioxidants and alkaline-based food. So that's so in China too, right? So we call this bitter melon, but in Japan, in Okinawa, it's called goya. And also a lot of our vegetables have purplish color. So that's from I think that can be connected to microbiomes. So that's a very, very hot topic. And also the weaving culture and also karate. And that's how we have a lot of European students. They came to OIS because they're very interested in martial arts and karate. It's not a joke. And so this is our campus. So we're a relatively young university, about 13 years old. And so what you're seeing here, so this is, now we have 5 buildings. So we started from 0. And this area, that's kind of student, postdoc, and faculty housing on campus. And so that's the beach. It's about 10-15 minutes walking distance downhill from campus. So that's why sometimes we organize group meetings at night. So Alex, I remember you had your group meetings on Saturdays at University of Washington. And So a little bit of history of our university. So it was funded by a group of people from the Japanese government, Minister Omi, and many Nobel laureates, and also some former university presidents from Japan. So Torsten Wiesel is a founding member. He turned 100 years old last year, and we gave him an honorary degree. So he got Nobel Prize in the 1980s. And also our first president, Sidney Brenner, was also a Nobel laureate, and he had a lot of connection, I believe, with Hong Kong, but more in Singapore. So you can kind of, so the concept was, it's really hard to break tradition. So in mainland Japanese universities, they have been trying to become more international, but there's always resistance to change, and it's just harder, a lot of inertia. So since Okinawa were kind of in a remote island, the government also decided to invest us as part of, kind of invest helping the Okinawa prefecture. So it's kind of similar to Hawaii. It's mainly focused on tourism. So they wanted to introduce technology and higher education to the local community. So that's a little bit of a background. And this is an overview of the history. You can kind of see the concept and the discussion started in 2001 and over the years, but in November 2011, that's when OIS became an accredited university, a graduate university. We only have PhD students. We do not have undergrads or master students. And every year we recruit about 50 students, PhD students. So it's a very small university. So our second president, Jonathan Dorfman, so he's a high energy physicist, was the former director of SLAC, connected to Stanford. And then the next president, Peter Gruss, was the former president of the Max Planck Society. So he's a developmental biologist. And then so more recently, in June 2023, we welcomed Karen Makidas. So she's Swedish, and she's an analytical chemist. She was the former president at Chalmers Institute of Science and Technology from Sweden. So we actually have quite a bit of Swedish connection as well. So you can see our adjunct professor, Svante Pääbo, received his Nobel Prize in 2022. So he has a small group at OIST. And in addition, so since I'm in this building, so I put this picture here. So Serge Harosh, so he has been on the board of governors for many years. So now I understand why he's so busy. He cannot be the chair of our board since he's the chair here as well. He continues to be quite active serving on our board. And what makes OIS unique, English is our operating language. And also it's a big deal in Japan. I don't know if there are any students from Japan, but in Japan, it's a little weird. The fiscal year starts in April. And also for all the universities, the students also start their semester instead of September, but April. I heard it's kind of correlated with the cherry blossom timing, just historically. And so as I already mentioned, we have a very a small kind of clusters of only PhD students. And so education-wise, a student to faculty ratio is quite desirable. So the government also has been investing us, offering high trust funding for creative, curiosity-driven research. And but one of the requirements is we have to make a significant contribution both to the economic growth in Okinawa and also in Japan. So the innovation is quite important as part of our growth strategy. Okay, so now moving on to the scientific part. So this is a quick outline of my talk today. So similar to Anderson, so I've been working on microfluidics and fluid mechanics throughout my whole career. So for today's talk, I want to show some of the the interesting microfabrication and imaging techniques we have developed after I moved to Okinawa. And then I want to share some examples and to show, so with creative platform design and fabrication, so it provides a lot of new opportunities for us to study either viscoelastic instabilities, which is so one example showing on the left, and also, so we're interested in microbial population in microscale. So the movie in the center shows neutral E. coli with the same fitness level, but just different fluorescent dye, so confined in a microchannel. It allows us to see how do they divide, how do they interact and compete with each other. So finally, so I want to use the last part of my time to discuss some of the biosensing platforms coupled with microfluidics and lab-on-a-chip devices for disease diagnostic applications. And so I've been very interested in how the flow of complex fluids and also organisms behave in the spatial confinement. So you can imagine this kind of flow in porous media, like how bacteria move in the soil, or how our cells and tissues behave in our body. And so that's kind of the motivation from a biological or process and biotechnology point of view. But on the left-hand side, you can see that this is actually a review article. So I'm one of the 23 co-authors, so led by Howard Stone's group, just to show how complicated it is. So when you introduce viscoelastic properties so into a microfluidic system, and what kind of instabilities can emerge. And they're also quite important, also relevant to biological systems and processes, for example, cell suspensions, blood plasma flow, so on and so forth. So, so in order to investigate a variety of interesting scientific topics, so first of all, so we have to make the device. And my students so once joked to me, like 2/3 of their time is trying to get the device working. And then they have to rush the last part of their thesis and to really answer the important scientific questions. So at OIS, we have a very good core facility, like the clean room and other fabrication facilities. At the moment, they're free to our internal users. So that's we're very fortunate. And being the provost, I'm responsible for that, so I want to keep that as long as possible. So that's my goal. And so we use a variety of different materials, such as PMMA, plastic types. So this we can just use laser cutter or 3D printers to make devices. Or PDMS, I think that's kind of for those who started working on microfluidics like 10, 20 years ago. So that's a very common technique using soft lithography technique. And so at OIS, we also have a couple good instruments. So one of them I will highlight here is so we can make all glass fabricated microfluidic devices. But as you can see, so different for different types of materials and fabrication techniques, they all have pros and cons. But for like biomedical applications, so we have been mainly using a combination of plastic and PDMS type devices. But for more complicated, smaller scale, if you require higher resolution, and if you have organic solvent, or if you really want to understand the flow behavior, and then using glass-based microfluidic devices more advantageous. So this is, so here we have another person from Seattle and University of Washington. So Kazumi is my lab manager. He's the only one I was able to convince to move to Okinawa with me. So his father is from Osaka, so that's the connection, but he doesn't speak Japanese. But he's a very talented engineer, and so he helped my group to start this kind of microfabrication by using selective laser-induced etching technique. And so the key actually component is actually at the design phase. And so you can use any software like a CAD or Blender and such to make intricate design. So on your computer, then you do the slicing. And then the next step is you use this femtosecond laser to irradiate a chosen volume, so in a fused silica or some other types of glasses. And then you put this glass block in an organic solvent and at a certain temperature and time. And so the trick is the etching rates are usually 1,000 times faster with laser modified region. So that will help us to create this kind of etch out the regions that we do not want, and eventually we can have this very nicely enclosed microfluidic device. But of course, you can also make like a dinosaurs, or this is a miniaturized beer mug, and this is a real pencil, just for scale purpose. So in terms of imaging techniques, so we use a lot of micro PIV setup to understand how things move around obstacles or corners and so on. And now we also have a system for tomographic imaging for a three-dimensional velocity profile. So in addition, we also use polarized camera and microscope for flow induced birefringence. So this is very helpful to study like protein polymeric solutions, DNAs, because the molecules are with a rod-like shape, and they tend to align with the flow direction. So with this technique, we can use the optics rules to so based on the alignment information to extract the local stress information as well. And in terms of the fluids we investigate, so it's a variety of different types of fluids, but usually they're viscoelastic in nature. So you can find like a saliva and ochre. So for a lot of these fluids, so both shear and extensional rheologies are equally important. And so in my group, we have quite a bit of expertise in this area for rheological characterizations and so on. And in terms of flow controls, so we usually we haven't done too much with digital microfluidics, but so we usually use a pump for flow control. And for complex fluids, besides the Reynolds number, so we also introduce other important dimensionless numbers, such as the Weisenberg number, elasticity number, that tells you how elastic the material is and how do they compete with, so how the elastic viscous force compete with each other. And so let me just show you a few different examples by using the glass-based microfluidic devices, and so what kind of interesting problems can we study? So in principle, so we're very interested in the flow behavior around corners, branches, and obstacles, and because they can translate also, so you can imagine we can view that as a model system to study complex biomedical problems like the fluid around your knee joints or around your lung and cardiovascular systems. But to simplify the system, we usually try to design benchmark flow configurations. And here are some examples. So we call this as a T-junction because this looks like a T, and a cross slot, so it looks like a cross. And so for each design, so we can kind of answer different types of questions. Like for T-junction, has been commonly used for mixing particle trapping applications. But for cross-slot, it has been used for enhanced also mixing and reduced drag. And so this is another type of device. It's a flow around like a cylinder. But the cylinder here is very long and narrow, almost like a glass fiber. So you can imagine that it can be translated to flow around like a cilia flagella type materials. So here are some kind of common examples and configurations we have been using. So the first example I want to show you, so with a special reason, because Sento is my second PhD student, And he's from Anderson Schum's group, was an undergrad. So I remember in 2015, I visited Anderson's group at University of Hong Kong. So I gave a talk, and so Sento approached me later, said, I wanted to apply for OIS, but I don't want to work for you. I want to become a neuroscientist. So I said, sure, because we don't have departments. And all the students, first year, they have to go through like 3 lab rotations. But at the end, so he tried two neuroscience groups, his first and second. But the third, he came to my group, he said, yeah, I don't think I like their methodology. He's like, I will settle with your unit. So I told him, are you sure? I don't think this is healthy. I'm just, you're settling with me. You should explore. But he ended up, so working in my group and has been very productive. And this is actually his first research project. So what you're seeing here is flow around, so at T junction, and Howard Stone's group from Harvard at the time, no, I think he already moved to Princeton. So they predict that, they call this vortex breakdown can occur from numerical simulations. But so Sento was able to capture this in real time. So what you're seeing here, so this is the T junction made of glass. And we can play with the flow rate on these kind of 3, so 1 inlet or 2 outlets. And by playing with the flow imbalance, which is captured by eye, so we can create this kind of tunnel. So we call this as like internal stagnation points. And so we can leverage this to, for example, for particle separation, cell sorting, and also capture or not capture certain elements at a given position. And so Sento received his PhD 2 years ago. So this is a happy picture. And ever since, so he has moved on to something quite interesting related to also connecting science with art. And so he's also a very established artist. So he's commissioned by like a Sony groups, with like animations. His work is displayed in the Times Square in New York. And he has more than 60,000 followers on Twitter, the most popular person of our university. So thank you, Anderson. And also Sento sent this picture and asked me to say hi. But he's also a big cat lover, so he cannot travel to Hong Kong. So here are a few kind of recent publications from Sento. Okay, and so that's with cross slot. Another example, so that corresponds to we call the cross slot. So what you're seeing here is, so we have 2 fluids. So they can be the same, they can be different. But here it's essentially exactly the same fluid, but to one side it's doped with fluorescent dye, so you can really capture how the interface evolves under different flow rates. And so what we're able to do is by using this the cross slot geometry. So this is a real picture here, and the major advantage for using glassed microfluidic devices is, so for those of you who are familiar with like PDMS-based microfluidic device, so you put the device on top of the microscope. But with the glass device, you can actually also tilt it vertically. So you can get a very full, comprehensive picture and how the flow behaves. And so this is a micro PIV movie captured. So this is water, and this is water doped with a very tiny amount of polymer, 10 ppm PEO. And so our observation at the beginning were it's kind of counterintuitive. If you focus on the Reynolds number and see when the vortex emerges, the critical Reynolds number actually for water is higher than actually for the dilute polymer solution. So this indicates that adding the polymer, small amount of polymer, actually induces the instability. But on the other hand, adding polymers also reduces the intensity of the vortex. And so that makes sense. And so we are able to to create this phase diagram. So we did a lot of experiments, and also we collaborated with Rob Poole from University of Liverpool for numerical simulations. So this map shows you, so the Reynolds number, that's kind of corresponding to the flow rate. The Weisenberg number on the vertical axis tells you how elastic the material is. So, so at the bottom half, so when the flow rates and when the Reynolds number is small, so the flow is steady, so you see this straight interface. But at higher flow rates, at moderate Weisenberg number, so we see this inertia-dominated instability signified by this kind of vortex formation. But at very high Weisenberg number, so you skip completely to this vortex formation, but transition into this kind of very unstable interface. They can be show periodic or non-periodic motion. So we can use this knowledge actually to for enhance like a drag reduction and other applications as well. So if you combine these two geometries together, so we can also find some biotechnology applications. So this is in collaboration with Aram Chang. I think Anderson Shum also knows him well. So he moved from RPI from the US to Korea University around the same times as me. And so this collaboration shows that when we design the cross junction connected with a T-junction, so we can trap the cell, so in the stagnation zone, like the movie here, and then we can also stretch it to open the pores of the cell membrane, and then introduce the drugs and other nanomaterials, and then let it just flow downstream. So we call this is the mechanical or spiral hydroporation in comparison to electroporation. So that's the traditional way you apply electric field. It's kind of execute the cells, so the survival rate is not very high. But this is more mechanical. So after they're being stretched, you just let them relax overnight, and the cell survival rate is about 95%. And so we also do quite a bit of studies of flow in porous media. And so this is important for polymer flooding, oil recovery, many industrial applications. But from kind of a fun problem, more fundamental problem, flow in porous media. So this paper was published by Jeffrey Guastro's group from Tufts University in 2020. So they reported that, so when you introduce disorder, let's say you start from this initial condition, porous media with this organization, and then when you introduce disorder by randomize the array to a small degree, they noticed that the instability is kind of disappeared. So they have this sensational title, disorder suppresses chaos. And so we got quite interested. We decided that we will start from a different initial condition. So this is our initial condition. We just rotated this in comparison to the top geometry. And then we use the flow-induced birefringence setup. And so this is a movie. So we observed something completely opposite from their observation. And so then our goal was to understand why. And so we're able to provide a unifying explanation. And so the key is the initial conditions are very important. So for their system, they started with the stagger system. And so with this geometry, so you have many stagnation points. They tend to block the flow path. So then when you tilt it, introduce disorder, it helps to clear the flow path. So it's easier, therefore, suppress the instability. But with our system, so if we start with a very well-aligned geometry with clear flow path, and then when you introduce some chaos or disorder, and then we're able to form this blockage and blocked flow path. So the key message is the obstacles imply stagnation points. And so it's all correlated to the number of obstacles and where they're located in terms of how do they interact with the flow. So this is actually a very fun paper. We worked this project. We worked on actually during the pandemic. So during also for the same study, we also identify elastic turbulence. So for those of you who are not familiar with this term, and for people in mechanical and chemical engineering, turbulence, we all know. So when you shake the fluids in a big tank, right? Typhoon. So those are turbulent, induced by inertia at high flow rates. But for fluids flowing at micro scale, the Reynolds numbers tend to be very small, on the order of 1 or smaller. But yet we observe the turbulence signature. And the reason is, so the elasticity, from the fluid introduces the nonlinear aspects. So therefore, we're able to, so this is the fingerprint when you plot the spectra. So when the power index is above minus 2.5, that indicates elastic turbulence. So our ongoing work is, so besides developing the microtomographic PIV, so we're also interested in introducing bacteria into these porous media, so we can see kind of collective behavior and the active entities and how do they interact and inside a small gap. Okay, so another example is related to fluid and structure interactions. So I have several unit members working on this. So first of all, flow around the cylinder, this is a very classical fluid dynamics problem. I think for undergrad fluid mechanics can be traced back to 1850s. So this is a benchmark problem to study viscoelastic fluids because it involves both shear and also extensional kinematics. So again, for complex fluids, we're interested in all these dimensionless numbers. And so in comparison to, so let's say when you make a PDMS devices, this is actually from my work when I was still at UW. So we use PDMS devices. So the micro pulse, you can imagine, it's like the pulse, it's very short and fat. So for that configuration, so we actually observe this instability occurring upstream. So this can be emulated almost to we call the constriction and expansion geometry. But on the other hand, so when your microcylinder is very long and slender, so the flow kinematics is completely different. So it's more important. So on the right is we have very strong extensional flow. So we're able to use our fabrication technique. So we're able to make a variety of different model systems. We can have one cylinder, we can have two, we can have an array. So let me just quickly show you some examples. And so the model fluid here is warm like a micellar solution. So it's a mixture of water, surfactant, and some salt. And so I think a lot of spray we use, this is from during COVID, so that's one of the main components. And so for this type of fluids, so they exhibit we call shear bending and also shear thinning behavior, so using the rheological terms. So the shear bending here meaning, so what you see, this is the viscosity versus shear rate. So they have this kind of a flat plateau corresponding to, so the viscosity is the same at a range of different shear rates. And so this introduces a lot of interesting kind of different types of time scales. So we can play with the time scales and how do they, from the fluid, and how do they interface with the time scale introduced by the flow, right? Convection, there's also diffusion, but for this problem, it's not important. But this is just kind of a summary. When you slowly increase the flow rates, so we observe this kind of instability behavior very different from like a supercritical pitchfork behavior to time-dependent transition. And this one is also quite interesting. When the flow rate is very high, we observe that actually the instabilities kind of diminish. And the reason is these very long, warm like micelles, so they're also very dynamic, not permanent, not like polymer chains. So they can easily be chopped off into smaller, shorter strands, so therefore making the fluid less viscoelastic. So we also progress to, instead of having one micropulse, so we have two. So this is 1 versus 2, so along the flow direction. And so let me just show you some of the flow-induced birefringent movies. So a different Weisenberg number, so you can see it's almost like a heartbeat. And so the frequency actually corresponds to the relaxation time of the fluid. So this is kind of exhibit, kind of shows how these the micropulse interact with the fluid. So the liquid strand, so over here, it's almost like a rubber band, like connected with the micropulse and having some feedback process. So we can do particle tracking and try to understand if there's any correlation between them. But ultimately, because we want to see if there's any connections between this and also our biological systems. So then we studied a more complex system. So we call this as canopy flows. So what you see is that for the canopy flows, that's very well studied among people in environmental engineering, civil engineering, like also ocean engineering, like a seagrass in the ocean, and also the wind, what you see, the movie flying over the rice field, grass field. And also buildings. But if you scale down the land scale, they can also be on the order of a micron size. So that's kind of flagellum motions, cilia motions, and so on. So we want to know if there's any common features. So between these two very different systems, but we call them as canopy flow. So a former postdoc from France, Charlotte, so she, so this is also, so during the pandemic, so she was able to figure out using kind of two photon microfabrication process, make these kind of micropulse arrays made of polymer. And then we can flow the liquid from left to right, also kind of like a saliva solution, not super viscoelastic. And under certain flow rates, so you will see, so we observe these really cool waves, kind of traveling waves, so intertwined, and so which is actually quite similar to this kind of large scale process. And so this work was published in 2023. So it's kind of interesting because we first actually submitted this to PRX, and we only had actually one negative reviewer. But Charlotte, as soon as the Japanese border opened, she escaped Japan because we had very, very strict border. So she was having a hard time at the time staying in Okinawa. So now I have a PhD student is kind of taking over of this project. Okay, so I have another, I guess, 10 minutes. So let me just quickly show you a couple more examples more related to biophysics and biological systems. And so this system is related to microbial population. And so some of you might have heard the term mother machine. So this is a very important paper published in 2010. So this group of scientists studied how can E. coli divide, proliferate. So in a microchannel, so basically in a tube. But so this one here, so one end is fixed, so one end is open, so they can only kind of be, the cells can only be expelled from the top. And also the nutrients can only be delivered by diffusion. So there are some limitations. And then University of Tokyo's one group, they reported this, they introduced this new design with kind of so the microchannel have two open ends, so the bacteria can get expelled from both ends. So inspired by that design, so my my first PhD student, Paul, so he's from Taiwan, and so he designed and fabricated, we call this multi-level microfluidic device involving glass, PMMA, and also PDMS. And so went through several phases, and it turns out to be quite challenging for long-term imaging, because so for one thing, bacteria they're easily get contaminated, And even when you introduce the tubing, if you're not careful, and then they form filamentation and then biofilm, then it explodes the entire device. And so our lens got destroyed twice. But over time, we're able to actually, using fluid dynamics knowledge, so using COMSOL to optimize the design, to ensure the hydrostatic pressure. So we're able to introduce the nutrient in the flow channel, and then the bottom layer, the bacteria, so that layer just for the bacteria to grow and also proliferate. So this is the example. So we're able to design microchannels with different width. Then we also observe, so they tend to form lanes in parallel to the flow direction. And so our collaborator, also a professor from OIS in biophysics, and developed this population model, and to understand what's their effective division rate under spatial confinement. So if you're interested, you can find these two papers here. There are also a lot of different movies you can find. So I currently have a student working on this. So now we're using strains with different fitness levels and see how do they interact with each other, and how do they react with kind of antibiotics and so on, for also kind of maybe drug discovery applications. Okay, so one last example is related to microfluidic biosensing platforms. And so this is actually a new area for me after I moved to OIST. And I got quite interested because a healthcare company, Sysmex in Japan, they just kind of showed up on my door and said, we wanted to fund you, and with a big commitment. So at the time, I didn't even have my lab yet. So I told them, hold on, but give me a year and a half after I set up my lab. So that's kind of the origin of why I got interested in also in this project. And of course, during COVID, I think all of us became experts in terms of biomarkers, biosensing, how to improve the, so to design a reliable detection kit. So there are four important aspects. So how sensitive they are, how fast you can get the results, and also how specific, how selective they are. They're related to false positive or negative results. And so this process shows how it works. So let's say if you're infected with a certain disease, and certain biomarkers will show up or will increase the normal concentration in our bodily fluids, such as saliva, blood, urine, and so on. And then you need some recognition elements that can capture the biomarkers. And so when that occurs, the binding occurs, we also need some signal transducers to identify. It can be either electrical signal or color-based, so on and so forth. So we developed in the past few years kind of label-free versus label-based signal. So ranging from kind of optofluidics, using localized surface plasma resonance to electrochemical sensors. So I'll just quickly give you two examples related to number 2 and 4. So for localized surface plasma resonance, so this is quite interesting. So it involves nanofabrication, applied physics. And so the measurement principle, so it's not new, so it can be traced back to this famous Lycurgus cup. When you shine the light inside and outside the cup, you see different color. So the pinkish color corresponds to gold nanoparticles embedded in glass, versus the greenish that corresponds to silver nanoparticles. And so we can use this kind of similar principle for the disease diagnostics. And so let's say if you have, or quantum dots, if you have a gold nanoparticle, you shine the light, you get a SPECT resonance peak. And then when antibody or some other entities bind, so you will get a wavelength shift, so on and so forth. So we can quantify this and build a calibration curve. And then for an unknown sample, so you go to this calibration curve depending on the wavelength shift, so you can correlate that to the concentration in the biomarker. But to make lab-on-a-chip devices, we have to make these gold nano or metal nanostructures at the device level. So we, instead of using e-beam lithography, so they're not perfect like e-beam lithography fabricated nanostructures, but they're sufficient to provide the nanostructures that can induce the surface plasma reaction. So by doing this, yeah, let me just fast forward. Here are some examples. So we develop various biosensing platforms for protein binding assay, nucleic acids, and biofilms, and so on. So this is an example. We use this to detect SARS and as protein fragments. But for the microfluidic device setup, it's very simple. We just made it like 3D printed with double-sided tape and connected with fiber optics. So this is the whole setup, and so it's quite accurate. Let me just show you the antibody against COVID-19 virus in diluted human plasma. So we can get quite high, very good limit of detection, and the assay time is around 30 minutes. And then we expanded this study by working with a professor from RICAN so he develops vaccines. So we call them multiplex biosensing. So I think it's, for example, nowadays, so we can detect whether, if you have a fever, whether it's influenza or COVID. Yeah, so I didn't get COVID until last June. So I went to the doctor, I had a fever. So I assume it's just influenza. But he used this multiplex test kit. So when he told me I had COVID, I was really surprised. I thought I was able to get through that. But I think nowadays the technology is quite advanced for this kind of detection platforms. So we can also use a similar concept and multiplex to, so we developed these prostate cancer diagnostic tools. My former postdoc now is a professor in Italy. And so this is, so for prostate cancer detection, it's very important because a single biomarker is not sufficient to tell you whether you have prostate cancer or not. So you have to use multiple biomarkers and see their detection within different detection range. So this is kind of the PSA biomarker detection. So I think I should probably, yeah, just finish here. I just want to highlight that for microfluidics, so it involves, I think it's a very highly interdisciplinary research field. And to make things work, so we need people in different disciplines in engineering, physics, chemistry, material science, and biology, and to work as a team and to push the limit. But so for my today's talk, the first half is more focused on fundamental fluid physics, and the last few examples is related to how can we use our knowledge gained from physics and fundamental science for to provide new technology, and there's tremendous potential. So before I finish, I just want to acknowledge my unit members. And so since Anderson told me CityU Hong Kong is the most international university in the world, and so I believe OIS is not far behind. So this is just my group. Over the past 10 years, I had students, postdocs from at least 30 different countries. And so unfortunately, I only had one student from Hong Kong so far. So I'm always looking for talents. We're recruiting both for PhD students and also postdocs. And as I mentioned, for some reason, historically at OIS, we have many European researchers and students, and a lot of them are very, very engaged with martial arts. So there's a kind of a little correlation. So with that, I thank you for your attention.
Thanks a lot, Amy, for a very wide-ranging topics in a short talk. So any questions from the audience? Yes, please, Professor.
Thanks, Amy, for the fantastic talk. Looks like you have done a lot of work since your last visit to Singapore.
Oh, thank you.
Yeah, it's very impressive. Your research group is very international. I see you have attracted a lot of people from different places in the world to come work in your group. Yeah. So next time, this time you have a very busy schedule. So next time, I hope you can come to visit our Department of Biomedical Engineering. So
yeah,
we do have
thank you. I would love to.
We do have a few faculty members doing work on microfluidics. Yeah. So talking about the last part of your research, biosensing.
Yes.
So you are using fluorescent label for detection, right?
So yeah, so we use so different platforms. We use kind of label-free or with labels. But for electrochemical sensors, I don't have time to talk today. Right. So that's kind of, we have to involve enzyme-based kind of reaction scheme.
Right. So we are also developing some microfluidic-based system for biodetection. But if it's a fluorescent-based, then we have to use either fluorescent spectrophotometer or microscope